Okay, so the algebra of numbers. Okay, the algebra of numbers that creates new functions. So the algebra of later we're going to talk about the algebra of functions, but this time it is the algebra of numbers that produces functions through those formulas, right? So you have input and you have maybe other numbers involved, and then you just combine them through these four algebraic operations, and you have your new function. So it's something specific in contrast to that problem that you have over there. So we're computing actual functions, and we create actual functions from inputs and other numbers. But we did start with the two simplest functions that do not require any actual algebra. Okay, so constant function, a number that is assigned as to the function, whatever it is. In that particular case, it's 2, and then whatever the input is, the output is 2. That's it. No algebra. Okay. The next one is called the identity function, which doesn't do anything to the output, but it does not throw it away. So the constant function does not take into account the output because the input because it doesn't matter. Okay, the output is always the same. This one, the input does matter, but you don't have to do anything with it. You just pass it along as the output. Okay, so that's the simplest, second simplest situation. Okay, so you may have to change units, but otherwise it is literally no algebra. And then finally we're getting to the next stage, and that is the stage of algebra where algebra is involved, and that is at the easiest. It is this. The formula is here. We are combining the input x with two other numbers through two simplest operations, multiplication and addition, or addition subtraction, just the same. So it's nothing new, but certainly notice that there is no division involved. We're not going to be doing division, it's just multiplication and addition for the time being. Okay, so the operation is very simple. You can write simply, you can put it in the form of a table once again, not a table, rather a diagram. So you first take x, then you multiply by m, step number 1, step number 2, add b. So multiply by m, add b. So in that order. Order matters, by the way. As you will notice, every time you have a list of instructions, the order of operations matters. So imagine that you first add b and then multiply by m. The answer would be different, right? So that is noticeable when you have a diagram. That is really right there in your face, explaining why. Showing that the order matters from x to then multiply by m and then to proceed to add b, and that way you get your output y. In algebra, it is less than obvious, and you have to do it carefully with reading algebra and knowing the order of operation in order to extract the same idea from the formula. So you have to remember, I talked about that when you read formulas, you read it from inside out, from x and then out. So x, then you proceed to expand it slightly, multiply by m, expand more, add b. This is the order of operations. Okay? So that was the initial algebraic approach of how it is computed, and then we did a little bit of geometry, and we spoke of the slopes. So m is called the slope, and so we have to explain what that means. Okay, so the slope is officially, or rather unofficially, is called rise over the run. It is the slope of a straight line. So before you actually start speaking of slope in a meaningful way, you have to say that, well, the graph is a straight line. Okay, so which is to be determined through pretty much experiment. And so every time you have a linear function, the linear polynomial, which is what it's called, mx plus b, the graph is a straight line. Okay, and that explains why it's called linear to be in the first place, because the graph is a straight line. That's the reason. Okay, so that is hypothetically just stepping back from that to understanding what the slope is, a straight line. Any 2 points chosen on the slope of the line, on the line, and then you divide rise over the run in that fashion, as you can see over there. and that was the last topic that we talked about. And did we resolve this issue on Wednesday? So so rise of the run appears to be about that triangle over there, this triangle that you can see. And it appears that we divide. Oh, yes, we did resolve it. And we and then the rise of the run is then seems to be a vertical side divided by the horizontal side. But what was the conclusion? Why it is not sufficient? What conclusions did we arrive to on Wednesday? What was the reason for why we speak of a run as the change of x and rise the change of y, rather than speaking of distances or lengths of the sides? Well, maybe we finished too quickly yesterday, so well, let's start over. So why is it not enough to think about speak of a triangle like I'm looking at, and I'm dividing one side, the purple side, by the vertical one by the green side, and then say that this is the slope? Why is it not enough for our purposes of studying functions with graphs represented by straight lines? The slopes can be negative. In other words, a typical situation is the rise is negative. So you can easily imagine that this is what the graph looks like, and in that case, if that is your graph, then the rise is negative, and so you cannot speak of lengths of triangles, because if I take this second case over here, the situation when we're going down, and as you can see, I'm looking at a triangle once again, then this will be its rise, and this is the run, and then if it is a triangle, then the sides of a triangle all have positive lengths. So, well, and then you would say that if I try to use that formula right there to that triangle over there, I will end up with again a positive number, and it would be, say, whatever it is, maybe this one is 1 and 1, and then the slope might be 1 again, which is simply not good enough. Then we will not be able to distinguish functions that go up and those that go down, increasing or decreasing functions. So, and that is a very convenient way of thinking about different behaviors of functions in terms of one single number, that is the slope. That idea goes all the way through calculus. So once again, one number determines whether a function is going up or down, and positive going up, negative going down. Okay, so then that's why it is preferable, by far, to speak of change of the variable and change of the other variable. Okay, and then that way the slope is in fact is the rate of change. The rate of change, that's what the rate is. So the rate of change of y, which is what output we're concerned with, relative to the change of x, and that's what the word rate is. One divided by the other, and we are dividing them. We just thinking of them in the literal sense as the change. So if the change could be positive, could be negative, depending which way we're going. So let me make that point one more time. So what we're talking about here. So once again, we could speak of nothing but 2 points and say this is A1, B1, A1, A2. So suppose we have 2 points, A1 and B1. Okay, so there is a graph somewhere, and we don't want to commit ourselves to any particular relative relation between the points. Okay, so now hold on a second. What is it? A1, B1. Where is it? To A1, B1, and here A1, A2, B2. Okay, so the first ones are on the x-axis and the second one on the y-axis. Okay, like this. Okay, so we have 2 points on the xy plane, each of which has 2 coordinates. So A1 is A1, A2, and well, there's no index here. A1 is A1, A2, and B is B1, B2. So once again, X, the first coordinate, Y is the second coordinate. Okay? So, and then once again, is there a line or no? There is no line. It doesn't matter. What we want to discuss here is the rate of, we are progressing. So move from A to B. The relative position of these 2 points is not important, or not that it's not important. We want to produce a formula that would not depend on their mutual position. Higher, lower, to the left, to the right, it shouldn't make any difference. So we move from A to B and then discuss change of X and change of Y. And they are simply the differences. Differences in the consecutive values. Okay, so then this is the change of X, and this is the change of Y, and I intentionally have an arrow there so that we know which way the change is happening. Okay, so the change, literally, A1 has changed from A1 to B1, so that's the change of X. Okay, so then literally the change will be B1 minus A1. So the last or the current value minus the previous value. Just the difference. And similarly, change of Y will be B2 minus A2. So as you can see, it is because we do subtraction, we in a way we are talking about how far apart these 2 points lie, but at the same time we do appreciate the direction of our change. So it could increase or could decrease. It doesn't matter. It works out the exact same way. Okay, and then based on that, we're finally moving on to understand the slope, and that is the relative rate of change. Slope, not the best way to describe it. If we're talking about functions, this is really not a way to describe it, because we are talking about the change of output y's relative to the change of input x, and here the word slope clearly relates to actual straight line. But anyway, so it's once again rise over the run, and change of x, change of y, vice versa. And so I'll just substitute, so it will be B2 minus A2, and B3 minus B1 minus A1. So once again, on the x, this is on the x-axis, which is the denominator, and on the y-axis is this. It is the numerator. So it is still, in spite of what we just talked about, the triangle is not to be forgotten. So it is the ratio of these 2 lengths, okay? And they are describing, the one way to describe it is to say this is the slope of that, let's say, black line, slope of this. But what is the meaning of this ratio? Looking at the triangle, if you remember from before. So look at the triangle on the right and tell me what is the meaning of that purple divided by green. I'm sorry, it should be the opposite. Let's start over. So the denominator is the purple one, this one. Okay, like this. So we divide the vertical by the horizontal. So what's the meaning of the ratio? This is a right triangle, remember, so that's the key thing about the Cartesian system, that the axes are perpendicular, which means all these lines that we draw will be perpendicular to each other, except if they have a slope. And now we have a triangle. It is a right triangle, and we divide one side by another one. That has a meaning from a certain field that you may have seen before. Ratios of sides of a right triangle. What?
Yeah, 1 squared 2 or something like that.
I'm not sure what you're saying.
Like a trig.
Yes, that's what I'm driving at. It is trigonometry. So I'm talking about trigonometry. And so what is it? Trigonometrically. Trigonometrically, this ratio is what? That's right. This is the tangent of the, let's say, base angle of this angle. As you can see, the opposite divided by the adjacent. That's the tangent for you. So, not to be forgotten, once again, this goes through a lot of calculus is based on that. As you can see, the idea then is applicable to, even though it is at its base, at its basic is trigonometry. Okay, it is, so it's about right triangles, but then we take it to the next level, and we're using this idea to study functions. So that's the point, and functions that are not only necessarily just a straight line that goes up, but rather any straight line that goes up or down. And in fact, we can even look at these 2 points in any order that we like. So so any 2 points taken on a straight line will produce the same slope. So the slope is not a geometric characteristic anymore, but rather it is a characteristic of a function. It just applies for the time being only to linear functions, but that's just a start. Of a function that has produced these points, just these 2 points. We have produced a certain characteristic of it because it is the rate of change, as I described, but also you can say it is in a way how fast it is growing. Right, so x's are the inputs, y is the output. So if we're comparing how fast the output has changed per change of x, it's telling you how fast the output is changing. So if you want to speak of if that function happens to represent, say, motion, then x is time, y is location, then you're literally talking about the velocity, the speed of how fast you're moving. But that could be applied to anything. If once again x is time, y is, say, temperature, then you can speak of how fast the temperature is changing, and so on. So that's the characteristic of it. So linear function is certainly a serious limitation out of all the functions that we can imagine. But imagine that a function looks like this. The function then is not linear, but it's made of linear pieces. And then for all those straight pieces, you can compute the slope. Okay, and then once again, you have a characteristic of a bunch of numbers, not one number, a bunch of numbers, how fast the function is growing for each particular location. So you may have been speeding up, start slow, then faster and faster and faster. That's the way, and you discover all of that from this computation to begin with. And then secondly, you are seeing it in the graph. So that ultimately, it's not ultimately, but at least an important purpose of a graph is to reveal something about the function that you may miss if you just do algebra. So you see a graph like that, you can say, well, look at the slope, how the slope is changing. So the slope is kind of shallow, then it's steeper and steeper and steeper. What does it mean? It means that we're growing, but not growing as fast early on than later, and then we speed up. So that little picture over there indicates acceleration. So acceleration, either literally you are driving and you are accelerating, or it is about accelerating any kind of process that is moving forward, and then it grows and it grows faster. Okay, linear function. But we stick with linear functions for the time being, and so there's only one number to worry about: the slope. So the slope of the function that relates to that particular function in fully, well, not fully, but there's also b, but it does characterize the function very, very much about the function. It tells you how fast it is growing throughout its domain, and or declining. So then you can see that the sign of m will determine that behavior, up or down. So let me make that picture, just make that illustration, that idea more tangible. It doesn't have to look like this. So the same exact formula as you're looking at might come from a picture that is a sort of kind of upside down. So let me make that picture. So like this. This is my function on the xy plane once again. And once again, I could choose a1, a2 here, a1, b1 on the x-axis, and then over here I have a2, b2. Okay, so no. Just decide which one point is the first, which one the second. So suppose this is the first, it's A, the second is B. Then I'll have a1. This is a2, the second coordinate of that point A, and this is b2. Okay, so we are progressing in that manner. Okay, and then at the same time we have change of x, which is this. Okay, if you want to keep simple, we just make the x change in the positive direction. After all, it is the input. It is entirely under your control. So just make sure that a1 lies to the left of b1. Okay. At the same time, I think I messed up. Okay. And then, but look at what has the way y coordinate is changing. It is going down. Right, so that's the opposite of what the previous example. So we are progressing along with the input. Input is still increasing, right? But now we ask ourselves what's happening to the output, and the output is decreasing. So that's a crucial difference, and we see it in the slope. So let's compute the slope using the exact same formula, except the tricky part is to understand the rise appropriately. So once again, this will be my 1, and it is positive. And here we have a decline. And I still want to speak of a rise. So the idea is simple. Decline is simply negative rise. Okay, does it make sense? Rise, negative is decline. What's the opposite of rise? Drop. So if you're dropping, then you are rising in the negative direction, and vice versa. So that's why the rise, even though it suggests going up, in reality, you just if the number that you're looking, you say rise is -1. What does it mean? It means that you're going down by 1. Okay. So that's the point of negative numbers, after all. So we don't have to worry about it. Have a different word for the situation that is almost exactly the same, except things are going in the opposite direction. So there is no separate slope, and there is no separate word for rise. It's still rise, it's still slope, even though we're going down. So we still speak of steepness, but once again, in the sense of the number that might be positive or negative. So steepness indicates then the high steepness means that you're going up fast. Low steepness means that you might be going down even fast. So this one is considered the slope is low slope, and you can draw it like this, and it will be still low slope. Why? Because slope is negative. So in that sense, in the sense of slope is negative. So because the slope, if the slope is negative, we're going down, and even if we're going down fast, and in the usual sense of the word, it means that that mountain we're sliding down is steep, but we say that the slope is however negative. Okay, so something to worry about. Okay, so let me take that formula again, and the formula applies fully. So I have still the triangle of mine, and I wanted to have a triangle, but I want to be careful because once again, this is the one side, this is the other side, and then if I just go ahead and divide these two, I will end up with a positive number because this one, is this positive? Of course it is positive. If you are looking at a literal triangle, then the lengths cannot be negative. It's a triangle. But if we're doing a Cartesian system, then every quantity that you can think of could be negative. Okay, so that's why we talk about distances. We're not speaking of distances. We speak of changes. We speak of displacements, if you like. If you want to still think in terms of motion, then you rather, instead of saying what is the distance that I have covered, you ask yourself, what is the displacement? That way, the positive displacement means they're moving in the positive direction. Negative displacement, you're moving in the negative direction. Okay, so everything, and then if you change in direction, you don't have to worry about that. Change direction, then I use a different word and have a different formula and have to worry about that. No need for that. So you have one number indicating in which direction you're going and how far, and could be positive or negative. So in that particular case, it reflects how fast we're moving, and it could be negative. So in this particular case, if I take my formula, then look at the formula at the top. It is B2, the B2 minus A2, which happens to be, in my case, let me rewrite it. So it is still the same formula for the slope. It is B2 minus A2 over B1 minus A1, and this one is negative, okay, even though the denominator is still positive. So numerator is negative, denominator is positive, so together, what do we say about it? It's negative. So negative divided by positive, it gives you negative. Okay, so it works out fine. Something that you can think about if you also are concerned about, what if we are at the bottom, we change our direction and start moving in the opposite direction along the x-axis, then the things won't change. It will both of the numerator and denominator will change to the opposite. So instead of B2 minus A2, you'll have A2 minus B2. And in the denominator, you have A1 minus B1. So both of them flip their signs, and therefore nothing changes. Okay, so that's a separate question that might require some extra thinking. But since we're talking about functions, then taking control of the input pretty much solves your problem, because you can make sure that variable is always changes in the positive direction, so always increasing. Okay, that way, and then the change of y will tell you everything, whether you're going up or down. Okay, so what else here is I wanna make a little point here about the domains, and the domains are typically we were speaking of. We did not speak of domains here for a simple reason, because the domain is everything. We did speak a little bit about that. All of these functions involve operations that do not have any trouble whatsoever in terms of the algebra. There is no division, there is no trouble. There is no square root, there is no division. So we cannot have anything problematic here. So the domain in every time is for all the functions that we have considered so far is negative infinity, infinity. So domain is, well, let's be clear here what we're talking about. It's the implied domain, remember? So if you start with the formula and then ask yourself about the domain, you are speaking of the implied or natural domain. And then you discover that since there is no division or roots or anything like that, the implied domain is everything. Okay, but it doesn't mean that we are somehow forced to use the whole real line. We don't have to. So it's possible then to take a smaller domain than the implied domain. The implied domain is the largest possible domain that you can have for this particular formula, mx plus b. Okay, but you can imagine that once again, no division. You can take smaller numbers, and so you can choose only integers for the domain. The only difference is that then your graphs will be made of nothing but dots. Rather than curves, they will still be aligned along a straight line, but there will be gaps all over the place. So if my domain is integers, then I cannot have a straight line anymore. I will have a bunch of separate points. Okay. So the point being is that the real line we don't really without actually looking into calculus and tools of calculus, we cannot speak of real numbers very comfortably because we don't really know exactly what they are. So what is square root of 2? What if x is equal to square root of 2? What is it to begin with? And what is happening to it if we plug it in as the input of our function? Well, if we just ignore that, possibly that's pretty much the choice that we make. We ignore the idea that there are real numbers for the time being and just accept them as just numbers that feel they have with no gaps, feel a piece of an object that all of the valid numbers are here, and then they are real numbers, and some of them are not integers or rational numbers for that matter. But it is a good idea to remember that you could do a lot with nothing but integers. So if you choose integers, then a lot of the things that we are talking about there will be still have the same value. So you can still speak of what these functions, linear function. You can speak of the domain. You can speak of the slope. So if the function looks like this, then there is nothing that's stopping us from finding what its slope might be. So you can even think of that not only the inputs are integers, but the outputs too. Like this. Okay, so these are also integers. Okay, and you can still ask yourself about the slope, what the slope is. The idea is naturally is the same, rise over the run. The only difference is by design, both the rise and the run will be integers. Okay. Integer and integer. Okay, so that certainly doesn't cover all the possibilities of functions, but it covers a lot. And what kind of slopes can we have? Now, that's the question. Integer divided by an integer, what it's called? It is a rational number or a fraction. So as you can see, even though you start with nothing but integers, if you start looking at the slopes, you're looking at division, and you end up with inevitably with fractions and generally rational numbers. So that is why we cannot really forever and stick with integers, because studying functions that it's like moving say 3 miles per 3 feet per 2 seconds. Every 2 seconds you progress 3 feet. Okay. Then what is your slope, or what is your speed? What's your speed? 3 feet. 3 feet every 2 seconds. What's the speed?
feet per second.
Yeah, 3/2 or 1.5 feet per second. Yes. So on so even though everything is measured in full units, the speed itself becomes fractional, and the same is with the slope, right? So if I have the picture would look like what, 3 per 2. So say how would it be, like 0, and then I move on by 2 seconds forward, okay, and then in the meantime I have covered 3 feet. Okay, so then these are the two consecutive locations are these. This one and that one. Okay, so I move exactly 3 feet per every 2 seconds, and the result is the slope is once again 3/2. Okay, we are eventually taking a broader view, and then that is that every x can be any number, not necessarily integer, not necessarily a rational number, but could be any real number, including like numbers like square root of 2 or pi or whatever. And then the same with m, same with b, and so that will require some extra work, but for the time being, this will do. So if we stick with integers, then slopes will be rational. So at least we don't have to worry about square root of 2 that comes from nowhere. Okay, so if I want to classify next, classify linear polynomials according to the slopes. It is still still steepness. So what we do is we ignore b. So you might remember what the meaning of b is. M is the slope. What is b? The y-intercept. Okay. So in other words, it is in fact much less important characteristic of the function. Why is it less important?
You can find that with the slope.
You can what?
You can find that using the slope.
No. You need both. If you have a function, you have both. If you want to find a function, you need both. Why would you say that out of the these two, we're talking about, we want to understand the behavior of the function, okay? And then what I'm saying is that m is more affect that issue more than b. Well, think about motion. Think about motion. Then if it is a motion we're talking about, then m is the speed and b is what? Not the distance, but rather your initial location. So at time x equals 0, you will be at b. So you're talking about then about motion starting at b and then moving at the speed of m. The speed is in a way more important characteristic than your initial location. So if you want to know how fast you're moving, it doesn't really matter where you started. Okay, so it will affect you how fast you're moving, how far you're going, are you speeding or not. So m is, in that sense, is more characteristic. And if you go back to functions, regardless of their particular meaning behind them, it's the slope is indicates the shape, not the shape really, but well, literally the direction of the straight line. Okay, so you can have a bunch of b's. So say slope is say. What is it? 1/2 here, and then, oops, and then if I change b, well, this is what's going to happen. Same slope, different y-intercepts. Not much is changing. You just move it up and down. So it's exactly the same line. It just shifted in the vertical direction. If you start changing the slope, however, then so let's take a look at it for the other direction. So suppose the y-intercept is fixed now. And now let's see at the picture, what if we start changing the slope? So y-intercept is given, and I'm changing the slope. So what's happening to those graphs, those straight lines? Yeah, they vary like this. So like this. It includes horizontal and includes down pointing down straight lines. So this is, say, y-intercept are different slopes. Okay, so so as you can see, indeed it's a translation or shifting of that piece of paper in case number 1. And for case number 2, we're rotating it. Okay, so covering all possible angles with the exception of what? We're covering all lines through that point with the exception of what line? The vertical line, because the vertical line has, that's right, it is actually the y-axis. So, so this one not on the list. Why not on the list? In the sense that there is it has no slope. Y doesn't have a slope, no slope, because slope is rise of the run. And what is the run for a vertical line? It's right. So there is no what the run is horizontal change. If we are on the vertical line, what's the change? It is 0, and so you don't want to divide by 0. So then there is no run, and there is no slope. Okay. So like I said, there's an exception, even though it is a straight line, definitely, and we spoke of it a little bit like a couple of weeks ago. Remember describing lines as relations rather than functions. But now we switch to functions and narrow it down, and then we have to exclude this function, this line out of consideration, and it has no slope. Otherwise, they're all here. So then I can actually classify as I promised. So let me I'll take that picture on the right, and I'll assign a number to each of them, which is the slope. So for example, this, let me maybe make a better picture here. So that is still my y-axis. This is my y-intercept. And then I have many lines starting from it, like this. I roughly divide in half each of these angles. You can certainly characterize them as you would outside of this class. Maybe in previously taken classes, you would characterize these lines based on simply the angles, right? They all have angles. So maybe we'll start with that and just write the angles. So say angle is what? What do you think? What's the angle? Looks like 45 degrees, yes. And the angle here? 0 degrees. Okay? Then it is, I'm not sure if you ever had to deal with the angles that goes down, then you would say that this one, his angle is negative 45 degrees. But that is pushing it a little bit. So instead, slopes will tell us the story. So let me just write those numbers that you don't have to worry about. So the 45 in between the lateral ability of 22.5 degrees, that one is you divide in half. And if you go up one by more, it is, what is it, 67.5, the next one, the steepest one. But with the slopes, the numbers are much simpler. So slope is what? What is the slope of this? At 45 degrees. Change of x and change of y. If this is 45 degrees, then what's the relation between the two? What? It is 1, yes. It is 1 because they are equal length. Why are they equal length? Because if it is 45 degree one angle, the opposite angle, or the other angle is also 45 degrees, so it's actually isosceles, and so the two sides are equal. So then what about down 45 degrees? What's the slope? Negative 1, right. So even though the triangle is kind of the same, once again, same lengths, but since we're going down, the change of y will be negative. Okay? And this one, 0. That's right. The slope is 0 because the run is 0. Run is 0. Well, I'm sorry. The rise is 0, but the run could be anything. So as long as it's not 0, so you end up with 0. The next one, this one is needs an explanation. So initially I just divided it in half, but let me make a specific angle here. So what if I have 2 by 1? If it is triangle with 2 sides and by 1, then this angle is also known. You might even remember what that angle is. 8 degrees, 30 degrees. Okay, so if this is 30 degrees, then what's the slope? So the slope, the angle is 30 degrees. The sides are 1 and 2. The slope is 1/2. Right. Okay, one more. This one. The angle is 60 degrees, and the slope is 2. Yeah. Okay. Okay, we'll finish this next time. There's some work to be done.